Okay, so I just wanted to make a quick video to make sure that you were seeing a lot of the things that I wanted you to see with these rational functions. So the first thing you had to do was complete a table where you have 6 over x minus 2. And if you do this, you should get negative 1, and then I think you get negative 6 over 5, and you get negative 6 over 4, negative 6 over 3, negative 6 over 2, negative 6 over 1, and you see the numbers are getting bigger or bigger in the negative direction, negative 6 over 0, and that is a problem, which we'll get to in a little bit. Then I think you get sort of a mirrored other side of it, where instead of negative, the answers are positive, 6 over 2, 6 over 3, 6 over 4, 6 over 5. And what's happening is these numbers are getting closer and closer to, they're getting bigger and bigger as you get closer to 2. And notice that in the denominator you have a 2. And as you get further from 2, notice the y values are getting smaller. So it's kind of the opposite of what we see in a linear function, whereas x gets bigger and bigger and bigger, y gets bigger. In this case, as x is getting bigger and bigger in both directions, y is getting smaller. Okay, and you get a picture that looks like this, and I think you get this general shape for what we're talking about now. It's called rational functions. At the beginning of the word rational is the root ratio. So a rational function is any function where you have a ratio of two polynomials, and think ratio, think fraction. And with the fraction, we get a denominator, and in the denominator, we're going to get these numbers that are forbidden. And the numbers that are forbidden in the denominator are the ones that make the denominator equal to 0. So this is the general format of a rational function, where you have A, B, and C. What we're mostly worried about are B and C. Notice that A will change the shape of the graph. And if you go from positive to negative, A is going to flip. Instead of being top right and top left, it's going to go top left and top right. Okay, so if A switches signs, it reflects it. And you could say it reflects it over the x-axis or it reflects it over the y-axis. That's what's kind of unique about these things. Actually, that's not true. It doesn't reflect it over the y-axis necessarily. It reflects it over these orange dashed lines, which we'll get to in a second. But B and C are the more important of these two parameters. A lot of times when we're graphing these things, I don't really care what this value up here, A, is, because it's only affecting the shape of the graph. I may care whether it's positive or negative, but that's probably the only thing I care about. B is important because B is shifting this orange dashed line left and to the right, and C is shifting this orange dashed line to the right and to the left. And what will the function ever reach these orange dashed lines, dotted lines, dash, whichever you want? Well, I put these things in there to show you that, like, as I get the orange dashed line in this case is at 2. So as I get closer and closer to infinity, which this is mimicking, I'm still getting a value just above 2. So if you imagine what's happening, if I just keep going further and further, notice when I start at 1, I'm at 3. When I end up at 1 billion, I'm still not at 2 yet. So it's getting infinitely closer to 2, but it never actually hits that. And on the other side, when I go to negative 1 billion, I'm getting closer and closer to 2 from the underside, but I never actually get to 2. And that's what the idea of a limit is. Okay, a limit is something that a function is going to approach infinitely or asymptotically, but it never actually gets there. And in this case, this is a limit that that y approaches as x goes to infinity. And we can also have limits as x goes to some constant number when y goes to infinity. So in this case, let's see, there's kind of a fancy way of writing this. And if I have a picture like this, The algebraic way of writing this is the limit of f of x as x goes to infinity equals 2. And I would say the limit of f of x as x goes to negative infinity is negative 2. And there's another concept of the limit as x goes to 2. In this case, watch what happens as x goes to 2 coming from the left side. What's happening to my function's value? What's happening to that dot? It's going down, 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 down. And the closer and closer I get to 2, the bigger being bigger negative, so the closer to negative infinity this number is getting, okay? And on the other side of the function, the closer I get to 2 coming from the right side, the higher and higher and higher and higher this number is going, okay? And if you think of what's going to happen when x gets to 2, it's undefined. It's undefined because you can't divide by 0. If I put a 2 in this denominator, I'm going to get 1 divided by 0. And you can't do that. And when you try to do that, you get closer and closer to infinity. So the way of writing this one is now this is a limit of f of x as x approaches. This gets tricky. This is notation heavy. In a normal year, I'd be teaching you this in bits and pieces, but in this year, I'm just kind of giving you everything, and then we'll take time to come back and unpack it all. But this is the limit of f of x as x approaches 2 plus. That plus means I'm coming from the positive side. This is the positive side. This is the negative side. It means I'm coming from the positive side or the right side. So as x approaches 2 from the positive side, I get infinity. As x approaches 2 from the negative side, notice that it's not going up, it's going down. So the limit of f of x as x approaches negative infinity, sorry, I did that one already. As x approaches 2 from the negative side, that means 2 coming from the left is equal to negative infinity. And that's a lot. That's the concepts of limits. These things, when you have a limit in a rational function, they get these orange dashed lines, and those orange dashed lines are called asymptotes. And so you can also say a function approaches this thing asymptotically, if you don't want to say infinitely. But it means you're going to get these orange dashed lines, and we're going to talk a lot about these orange dashed lines. And the last thing that I included is that an orange dashed line could be vertical, like it is here. It could be horizontal, like it is here. And also there's times when we might even get a asymptote that's not either horizontal or vertical. It's slanted. And so these ones are called a slant asymptote, and I don't know exactly. It's somewhere around here, and you notice that the function approaches that line. There's a vertical asymptote in this one at x equals -3. But the function approaches that line as you get further and further from -3 on the left and the right. Okay, so that's a lot. We'll be unpacking and going over this stuff slowly, but hopefully that's somewhat helpful to map out all the stuff that we need to know about rational functions.